Okay, so let's start. Can everyone read this www dot whatever is written there? So if you missed a lecture or you want to review a lecture for preparing for the test, the lectures are on this website. The lectures are on this website. So yes. Oh, then I have to type 20. Well, I have to type 45 emails. I don't know. See, okay, I can read it for you. So it's www.vbs Virginia Boy System or Sister .vt.edu /content /classes /display _ class dot P as in Peter, H as in Harry, P as in Peter, question mark, course _ uppercase I, uppercase D as in David or dog, equal sign 9286720008. Yes.
Just email that to I think I just sent it to the whole class, but I'm not sure. So
Oh, okay.
I want to check.
So did you get it? Okay, so he did the work for me. So he did me a favor, Pierce did me a favor and sent it to the entire class. So you should have it. Okay. So in case you wish to review something, okay, please know, I think one of the rules of the class is that only I am allowed to talk and you will talk only if I ask you to talk. Okay? I think that was the first day assignment, the first day I distributed syllabus. It said, you will ask me questions, you will not ask your neighbor a question. Okay, so that's part of the agreement. So you should honor it. So if you wish to review any lecture, as far as I know, there is no editing. So whatever we discussed in the class should be on the tape. I tried to play one this morning and it seemed to work. So that was the last lecture I taped. So it has by date. So it tells you, well, it doesn't tell you the content unless you click on it, but you can click on it. I do not know if it requires Virginia Tech ID or not. It did not ask me anything. So, I mean, that's only for Wake Forest people. If they have difficulty in accessing it, then we will have to make some arrangement. Okay, so any question you want to ask?
This is regarding the test.
Okay.
What would be the preferred notations in the test? Suppose if there is a problem with where I'm supposed to prove something, can I prove that using, say, matrix notation, or I have to use index notation always?
Yes, you can use either index notation or direct notation or matrix notation. All of them will carry the same credit. Anything else on your mind before we start? Okay, so what we were studying was what is the property of the skew symmetric tensor W or the spin tensor W. So what if n, a unit vector n, is an eigenvector of the strain rate tensor D, then Wij nj equals n dot. So the spin tensor operating upon the eigenvector of D, not any other vector. An eigenvector of D will give you the rate of change of that vector. Also, we know that since n is a unit vector, therefore ni is 1. And if you differentiate this with respect to time, we will get ni dot equal to 0. So you get twice of that, because it's ni dot ni plus ni dot equal to 0, but 2 drops out. So what does this tell us? This says ni dot is perpendicular to ni. This one is true for every vector, that the rate of change of a vector is orthogonal to the vector itself. The time rate of change of a unit vector, the time rate of change of a unit vector is orthogonal to itself, is perpendicular to itself. So if we combine these two, then what we get is Wij Nj equals alpha Ni perpendicular. This perpendicular sign means that Ni is orthogonal, Ni perpendicular is orthogonal to Ni. And alpha is a constant. This equation does not say that Ni dot is a unit vector. Actually, Ni dot has units of per second. Ni is a unit vector. Its time rate of change has units of 1 over second. Okay? So the vorticity vector or the vorticity tensor or the spin tensor operating upon an eigenvector of n, eigenvector of d, operating upon an eigenvector of d gives you a vector that's perpendicular to the eigenvector of d. So, and d has, generally speaking, d has 3 eigenvectors and 3 eigenvalues, and they can be chosen to be mutually perpendicular. So what happens then is that spin tensor will transform an eigenvector of d into some other eigenvector of d. Eigenvectors of d are they can be chosen to be mutually perpendicular. So one interpretation is that the spin tensor transforms an eigenvector of d into a different eigenvector of d. Okay, so we talked about the rate of change of length. So we have talked about dxi dot being equal to Lij dxj, where Lij is the velocity gradient. So Lij is the velocity gradient. Now the question is, what is the rate of change of volume? And what is the rate of change of area? So first volume, which is easier, and then we will talk about the area. So we have already talked about the rate of change of a line element or a vector dxi. So the next question is, what is the rate of change of volume? So we know that little dv equals j times big dv, where j is the Jacobian. J is determinant of f, yes.
Is this volume or velocity now?
Oh, sorry. Okay, this is for volume. So this is for volume. So if you take the time rate of change, we get j dot dv plus j dv dot but the rate of change of volume element in the reference configuration is 0, because volume element in the reference configuration is fixed. So this quantity is 0. And we proved that j dot equals we showed that j dot equals j. This is velocity now. Velocity has components. Volume does not have any components. So this is delta Vi over delta Xi, which is the same thing as dii. But what is this quantity now? J times big dV. That's the volume element in the present configuration. So this is equal to dii little dV. So the rate of change of volume per unit volume is dii, which is same thing as delta Vi over delta Xi, which is same thing as first invariant of D. It's D11 plus D22 plus D33. So that's called the first invariant of a tensor or a matrix. This is the sum of the diagonal terms. And that will also equal the sum of the eigenvalues of D. Okay? This will also equal the sum of the eigenvalues of D. So the rate of change of volume per unit volume, you may think of saying is volumetric strain rate. Its rate of change of volume per unit volume equals D11 plus D22 plus D33, or sum of the eigenvalues of D. And if the material is incompressible, or if the body is made of an incompressible material, then what will be dii? 0, because dV dot is 0. Okay. So what about the area element? So that's the next one. Is there any? I think you have a question.
Can you put that back up for a minute?
Yes.
The dvi, dxi, those are both partials, right?
Yeah.
The d's they're
Oh,
just different.
sorry. Yeah, that was, yeah, it is partial, right? Yeah, my mistake. This was supposed to be partial, not D, but partial derivative. Yeah, thank you. Okay, so now if we look at area element, so that equals J F inverse Li area element in the reference configuration. So there is a summation on uppercase L. Uppercase indices indicate components in the reference configuration. So this is area element in the reference configuration. On the left hand side, we have area element in the present configuration. So take the time derivative because we want to find its rate of change. So the area element can change because the direction is changing, or the area itself is changing, or both are changing. Use the chain rule of calculus. So you get J dot F inverse Li dal plus J F inverse Li time derivative of this dal. The time derivative of d uppercase A is 0. So this is again using chain rule of calculus. Like this is a function product of two functions. Third one is not a function of time. So the derivative of first times the second function plus first function times the derivative of second. Does it make sense? J dot we know is J delta Vi over delta Xi, and this V is velocity. F inverse Li dAl plus the second term. So we need to find the time derivative of F inverse. Anyone will like to venture a guess how to find the time derivative of F inverse? We need to find the time derivative of F inverse. Okay, so I'm going to write here and then I will copy the result. So F inverse is identity. So differentiate both sides with respect to with respect to time. Differentiate both sides with respect to time. So we get F dot F inverse plus F inverse dot is 0. Okay? So F dot F inverse, I transfer this to the other side. So I have minus equals F inverse dot and pre-multiply by F inverse and we get F inverse dot. And Michelle, is it okay? You don't seem to like it, but I mean F inverse is identity, so differentiate both sides with respect to time and then transfer one term to the left side. So now pre-multiply by F inverse and we are done. So we have minus F inverse F dot F inverse equals F inverse dot. It's very similar to if you differentiate 1 over x or x to the power minus 1, you get 1 over x square x dot. So you have F inverse, which is roughly speaking F minus 2 times F dot. The only thing is you have to be careful about the order of multiplication. So I could not have written F minus 2 times F dot. Okay? If you differentiate x to the minus 1, which means like 1 over x, you get minus 1 over x square x dot. So we have minus here. We have F inverse, which is like F to the minus 2, F dot, except that you have to worry about the order of multiplication. Okay, so now we want the components. So this is F inverse Li dot okay, we want the component form. So this is minus F inverse. So you start with L, so J, F dot J M, F inverse M I. It's multiplication, so the summed index should be next to each other. And now we substitute that in. Oh, but I have a slight problem in the previous equation. I is there 3 times, which is nonsense. So I should really change this I to j. So in the previous equation, we had written j delta vi over delta xi, but I happen to be there 3 times, so it makes no sense. So this first term should have been delta vj over delta xj. And if I did that, now I am in trouble here because I have j and j. So I can't quite copy this thing right there. Oh, but I have a plus sign, so that's okay. This is going to be the next term. Okay, so plus j, f inverse li dot, so that's this one. So I have minus f inverse l j f j m f inverse mi. Oh, this is a dot here, and dal. Is it making sense? So we have dai dot, this time rate of change of the area element, is j. The first one, let me combine these terms. What is this equal to? It's already the first line on the chalkboard or on the screen. So it's a DAI. So we have delta Vj over delta Xj DAI. Then plus and minus, so that becomes minus. And now if we look at this term, so if you look at this term in the box, that's equal to what? Daj. And what about the other two terms? F dot F inverse. That's velocity gradient. L is F dot F inverse. So that's L J I DAJ. DAJ. Okay, so DAI dot equals delta VK over delta XK. Delta Vj over delta Xj is the same thing as delta Vk over delta Xk. So I'm changing that J to K. Okay, and the next thing I'm going to do is change DAI to delta Ij DAJ, which is the same thing still as DAI. The reason is I want to take DAJ as a common factor. So minus LJI DAJ. So now I can take a common factor and I get delta Vxk over delta Xk delta Ij minus delta Vj over delta Xi Daj. So the time rate of change of an area element equals delta Vk over delta Xk, delta Ij minus delta Vj over delta Xi dAj. Okay. So it includes both the change in the area, the rate of change of area, plus the rate of change of its direction. So the area element the time rate of change of an area element can be due to either the change in the area itself, or the change in the orientation of the area, or both. So any question about this? So the velocity field contributes to the rate of change of area. Remember now, this term Lij or Lji is sum of both d and w. So both strain rate and spin contribute to the rate of change of area. Both the spin tensor and the strain rate tensor contribute to the rate of change of area. The first term, delta Vk over delta Xk, that's only coming from the strain rate tensor, because Wii is 0. The diagonal components of the spin tensor are zeros. So this thing is only d11 plus d22 plus d33. But both d and w are in this term. Okay. The next question that comes up is the following. So we learned, and I hope you remember, that F equals Ru. That was the polar decomposition theorem. The polar decomposition theorem said any deformation, any matrix actually can be written as the product of an orthogonal matrix and a positive definite matrix. So is W, the spin tensor, equal to R dot? Okay. Also the question comes up, does B equal E dot or epsilon dot? Does the strain rate tensor equals the rate of change of strain? And we learned two tensors that describe the strain. One was E, capital E, which we called Green Saint Venant strain tensor, and the other one was epsilon, that we called Almansi Hamel strain tensor. I don't know if you remember those names or not, but a week from today you should remember them because we have a test. Okay, so let's try to answer that question. Are these things equal? So what is F dot? F dot is R dot U plus R U dot. Again, chain rule of calculus. L, the velocity gradient, is F dot F inverse by definition, and we proved that. So L is F dot F inverse. So that means is R dot U plus R U dot F inverse will be R U inverse. So F inverse will be R U inverse. But L is B plus W. L is the symmetric part of velocity gradient plus the skew symmetric part of velocity gradient. any tensor can be written as the sum of symmetric and skew-symmetric tensors. So this is strain rate, and this is spin. So that equals R dot U. This U inverse, when you take R U inverse, that's going to give us U inverse R inverse plus R U dot U inverse R inverse. So what is R inverse equal to in terms of R? R transpose. Because R is an orthogonal matrix, so its inverse equals its transpose. And U inverse is identity. So this one is identity, like 1. So we get R dot R transpose plus, I'm going to write this thing as 1/2 plus 1/2. I'm going to write this thing as 1/2 plus 1/2. Okay. So leave some room. So it's R U dot U inverse and plus 1/2 R U dot U inverse. And now I'm going to add U inverse U dot and subtract U inverse U dot. I added this term, I subtracted that term. So it's balanced. Nothing, we have not changed anything. It's still equality. Does it make sense? So we wrote this term as 1/2 plus 1/2. We wrote this term as 1/2 plus 1/2, and then we added this and subtracted that. So everything is balanced. Now, I need to show you that the R dot R transpose is a skew symmetric tensor. So to show that, let's look at R transpose, and that's identity. R is an orthogonal matrix, so its transpose equals its inverse. And I have put Tim Hartman to sleep. Sorry, it's all algebras. What can I do? All I'm trying to do is show you that W is not equal to R dot, and D is not equal to U dot. Then I will show you D is not equal to E dot, because sometimes you might, in writing, you might say strain rate, you might say rate of strain. These are not same things. So that's the whole idea of showing you that D is not equal to E dot. So you have to be careful whether you are writing strain rate tensor or rate of strain tensor. Some books are loose. They use the terminology, or some papers use the terminology rate of strain tensor. But that's rate of strain generally implies you are differentiating strain. If you say rate of strain tensor, it implies I am differentiating strain tensor with respect to time. But that's not what strain rate is. Strain rate tensor is. That's the whole idea of showing you, except for small strains, which we have not talked yet. If you are talking about small strains, then you can confuse things. You don't lose much. Okay, so if we differentiate it, R dot R transpose plus R transpose dot is 0. Therefore, R dot R transpose equals minus R dot transpose. Time derivative of the transpose is the same thing as the transpose of the time derivative. Time derivative of the transpose of a matrix is the same thing as the transpose of the time derivative of the matrix. So this thing is then minus R dot R transpose transpose. So what it says is that this matrix equals the negative of its transpose. So these two are same. So the matrix equals negative of its transpose, or if you take the transpose, you get negative of itself. And that matrix is called skew symmetric. Okay? So now we go back here. We go back to the equation we derived. So this term is skew symmetric or anti-symmetric. We just showed. This term, the one I just underlined, is also anti-symmetric. Because if you take its transpose, you are going to get the transpose of all of this. This R transpose will come here, this R will go there, but inside terms, you will get a negative sign. See, this says U dot U inverse, this says U inverse U dot. When you will take the transpose, the sign of this term will change. Now, if the sum of a symmetric matrix and a skew symmetric matrix equals the sum of a symmetric matrix and a skew symmetric matrix, then symmetric matrices must be equal and skew symmetric matrices must be equal, which means that D, maybe I should have written W, so W equals R dot R transpose plus 1/2 R U dot U inverse minus U inverse U dot R transpose. So the underlying green terms are equal. And it's clear that W is not equal to R dot. W is not equal to R dot. For W equal to R dot, R has to be 1 and U dot has to be 0, which is a very special case. So the spin tensor is not equal to the rate of change of the rotation matrix that appears in the polar decomposition of F. The spin tensor is not equal to the rate of change of R. So W is not equal to R dot. This is in general. There may be special deformation for which it may be true. There may be a special case for which W might equal R dot, but we are talking about in general. Okay? And by the same token, the same equation says D is 1/2 R U dot U inverse plus U inverse U dot R transpose. Don't worry, I'm not going to ask you to prove this in the exam or the test. So if those of you who are overly concerned, how will we prove this in the test? I will not ask you to prove it in the test. But those of you who are doing PhD and those of you who are in biomechanics, you will be dealing with large strain problems. So will other people who are doing in armor. If you want to study penetration of armor, same thing. We are dealing with large deformation, unless the armor happens to be say, polyethylene fiber or dyneema, then it's different. Okay, so D is not equal to U dot. D is not equal to U dot. That's what this exercise shows. However, the question we asked was, is D equal to E dot or epsilon dot? And the answer is no. So let's show that. And I will show one of the two, and the other one you can read in the book, if you like. So let's try with, say, E. 2E is C minus 1, and C is F transpose F minus 1. C is right Cauchy-Green tensor. The reason C is right is because C equal to U square, and U is on the right side in the polar decomposition of F. If you recall, this is also equal to VR, and B equal to V square, and B is the left Cauchy-Green tensor, because V as in Victor is on the left side of R. Okay, so what is 2E dot? So that's F transpose derivative F plus F transpose F dot. Derivative of 1 is 0. But F dot, F inverse is the velocity gradient. So that implies that F dot is LF, post multiplied by F both sides. And if we substitute in this, so we get LF transpose F plus F transpose LF okay. So this is then F transpose L transpose F plus F transpose L F, and now we are in business because F transpose is a common factor, L transpose plus L times F. I think it's a fair question to ask, does it D equal U dot always? Now keep in mind, when you read the questions, read them carefully. Please read the questions carefully. There may be terms like always, never, forever, so you have to be careful when you answer those. And the answers may be true or false, so there is no partial credit. What can be a partial credit? If you say the answer is out of true or false, you choose the wrong answer, there is no way to guess whether you knew it or you did not know it. You cannot say I knew but I checked the wrong box. So I'm afraid, so that's the disadvantage of such type of questions. Right? Okay. On the other hand, they are quick. You don't, either you know it or you don't know it. You cannot say I made a mistake in algebra and so on. So there will be several of those questions. Several. Several means many. Numerous. Certainly more than 3, 4, 5 words. Okay. I did not mean 345. but certainly more than 10. Okay, so there will be true, false, yes, no, or some questions like you have to write one line or 2 lines. So be careful, okay, and read them carefully. Read the questions carefully. You cannot say, I did not read the last word which said always. I did not read the first word which said generally speaking. So be careful, okay? And most of you know English better than I do, but you have to read the question paper carefully. So, okay, so what is this L transpose plus L? What is, see, we just wrote L was equal to D plus W. So L transpose will be D minus W. So this is 2D. So this is twice F transpose DF. So we have 2E dot equal to twice F transpose DF. And 2, of course, cancels from both sides. And you can see that E dot is not equal to D unless F happens to be 1. See, if F is equal to 1, then E dot equal to D. So when will F be 1? When will F be 1? In the undeformed state. Very good. See, F is 1 in the undeformed state. So only in the undeformed state, that means at the initial time, when you start your clock or when you start your test, is E dot equal to D. As soon as even a microsecond or a nanosecond or a femtosecond passes, E dot is not equal to D. How much the difference between the two is depends upon F. So it depends whether F is large or F is small. Okay? So since we are saying large or small, now what do we mean by large or small? So if you recall, twice of EAB equal to UA comma B plus UB comma A plus UI comma A UI comma B. So it's a sum of 3 terms. Is sum of 3 terms. This last term, the last term is the troublesome term. Okay. This term is the one which is making the strain. Strain is E. UA comma B is displacement gradient. Is the gradient of displacement. So the strain displacement relations are nonlinear, and that's because of this term in the box. The strain displacement relations are nonlinear because of the term in the box. Now, if UA comma B is of the order of, this is big O. If this is of the order of epsilon, this really means there are 9 components of UA comma B. A goes from 1 to 3, B goes from 1 to 3. So UA comma B has 9 components, 9 values. This order of epsilon means the following. This big O, not small o. Small o has a different meaning. So big O means, so if you divide this by epsilon and take the limit which I think you learned in first course in calculus, how to take the limit of something. So if you take the limit of this quantity, you get a constant, which is not equal to 0. Well, 0 is a constant too, but you get a non-zero constant. So what will be the first term if I expanded this into, supposing I expand UA comma B in Taylor series. And I think you know Taylor series, right? Actually, you had an exercise in homework number 1. There was a problem, expand log of x in terms of Taylor series or some other function in terms of Taylor series, right? So if I expand UA comma B in terms of Taylor series and I have this condition, so what will be my first term? Well, this you learned in calculus, right? If I expand UA comma B, and the answer is really on this screen. UA comma B is of the order of epsilon, and the definition of the definition of the order is given there. So if I expand in terms of Taylor series, what will be my first term? Yes, Ganesh?
Epsilon.
Pardon?
Epsilon.
Oh, epsilon, yeah. So it will be some constant times epsilon. And the second term will be then epsilon square times some constant. Of course, this is a different constant from the first one, and so on. So if epsilon is much, much less than 1, no, this is what, just one more minute, then I will quit. This is the notation we use for much, much less than 1. I mean, English language I don't think we can use the word much, much less than 1 because it doesn't mean much. However, what we mean here is such that square is negligible as compared to the first term. Like epsilon square is negligible as compared to epsilon. Epsilon square is negligible as compared to epsilon. Then we say that we have small strings. So if UA comma B is of the order of epsilon, where epsilon is a number considerably smaller than 1, then we say that our strings are small. Okay, so we will pick it up from here. And you will see life is much simpler for small string theory.
If you took the integral of B with respect to time, would that equal U?
No, that's the whole idea. If B is not equal to U dot, then its integral will not equal to U.
So is it like a problem in that one is from the deformed states to the undeformed states?
So B is the rate of change in the present configuration, and U is in the undeformed state. Sure. Oh, let me think. I will tell you Friday.
Frame rate in the undeformed configuration?
Actually, there is no, you cannot define strain rate in the undeformed configuration. Yeah, you are.
The very first sheet of today's class, there was something you wrote n, and then there was a perpendicular sign. On
That
top
means
of it.
that's a vector perpendicular to n. It's a different vector from n.
But that is not a unit vector, right?
No. No, it's not necessarily a unit vector. It may be, but it's not necessarily a unit vector. All it says is, yeah, but if you take the time rate of change of a unit vector,
That may not be a unit vector.
all it says is perpendicular to the vector n you started with, but its magnitude can be anything. Mission? I don't have to carry it then.